So, welcome everyone to the NPTEL course on Food Science and Technology. This course is instructed by Professor H.N. Mishra sir, who is in the Department of Agriculture and Food Engineering at IIT Kharagpur. And I am I am Shikha Sharma, and I am a teaching assistant, and I am also a research scholar in the Department of Chemical Engineering, IIT Guwahati. So this week live interaction session is for week 10, and the assignment submission deadline for week 10 is basically 1st of April. So please submit on time. So the topics that we will be discussing in today's class will include the module 10, which is about food formulations and processing. So it includes basically the topics like food process operations and principles, ingredient preparation, formulation, and metering. Then mathematical tools for food formulation, new product, new food product development, batch and continuous processing, functional and designer foods, and 3D printed foods for personalized nutrition. So it includes basically 5 lecture videos from 46 to 50, and lecture 46 is all about food process principles and operations. Then 47 is about food formulations and the design. 48 is about mathematical tools for food formulation. And 49 is about functional and designer foods. Lecture 50 is about 3D printed foods for personalized nutrition. So I hope you have gone through these 5 lecture videos in which Professor Mishra has uh, discussed about in detail all these concepts. So let's discuss some of the. So today's live interaction session will be based on the mixture of the questions, both the conceptual based and the numerical based. So uh, if you have any doubt from previous lecture videos, or if you have any doubt in the today's class, so feel free to ask. Okay, so let's begin with today's first question. The first question is about the Kick's law. So which of the following statement is are true with respect to the Kick's law? So first statement is energy required for size reduction is proportional to the particle's initial size. Second is energy required for size reduction is directly proportional to the new surface area created. Then option C is work done in size reduction is proportional to the square root of the particle diameter. Then D is energy for size reduction depends only on the product size. So we know that we have this size reduction laws. We have three: Kick's law, Rittinger's law, and Bond's law. So we need to here we are discussing here about Kick's law. So we are discussing about its energy required or work done. So there is formula regarding it. So anyone who would like to tell what energy, so the energy, how is it proportional to the or is it directly proportional or inversely proportional to the dimensions of the particle? Shiva is saying A and C. Anju A. Okay, so let's discuss the solution. So option A is correct here, that the energy required for the size reduction is proportional to the particle's initial size. So basically the Kick's law is telling that it is stating that the energy required, which is for reducing the size from suppose this size of the particle to smaller size, if we are reducing the size of the particle, so the energy required to do so is basically directly proportional to the particle's initial size. So this law is particularly useful for coarse grinding operations where size ratios are more significant than the surface area changes. So E is equals to Kk, which is basically this K is Kick's law constant, and multiply into ln xp by xf. So xp is the particle size in the product, final product. This is small size of the product, and xf is basically the particle size of the feed, which is the initial size of the particle, which is the coarser one, this one. So basically for particle size, we are taking, since we are considering here that the particle is of the round shape, or is it as it's a sphere. So we are considering that the diameter is basically xp of the product and xf for the feed. Basically, Rittinger's law, the second law we talked about is Rittinger's law. So Rittinger's law states that the work used for the particulate size reduction is directly proportional to the new surface produced, and it is, this law basically is used for the fine grinding of the particles where the large increase in the surface is there. So here the new surface area is created, or the law which is related to the surface area is mostly the Rittingers, because here fine grinding we are doing and more of the surfaces is exposed. That's why the Rittinger's law is applying, we are applying here in fine grinding, which says that energy is equals to, this is Kr is the Rittinger's constant into 1 upon xp minus 1 upon xf. So 1 upon xp means that the 1 upon the final product diameter minus 1 upon the initial or the feed product diameter. Then next is the Bond's law, the third law, which states that the work used to reduce the particle size is proportional to the square root of the diameter of the particles produced. So it is used for intermediate grinding process. So here P by F, which is divided by power divided by anyone? What is F here? Feed, right? Equals to 0.3162 into W. W is work index, multiply by, this is in brackets. So divide by, multiply by 1 upon square root of xp. Xp is the product diameter in mm and xf is the feed diameter in mm. So this is basically the square root of the diameter of the particles, and the requirement in kilowatt hour per ton of the feed, which is this F, feed rate, needed to reduce a very large feed to such a size that 80% of the product pass through a 100 micrometer of the screen. So what we are considering here, when we are grinding the coarse particle into the finer particle, so what should happen? The 80% of the particle should pass through the sieve of 100 micrometer screen. So we can considering, if 80% particles has already passed through that screen, and so 80% fine particles or grinded particles will be of that particular size. So then only we will considering that particular diameter. So here if we see the square root of the particle diameter, this is about the Bond's law. So first one is basically more related to Kick's law here. Then fourth option is saying that energy for size reduction depends only on the product size. So it is not true also that the energy only depends on product size. It depends on other factors also. That's why we are using this Kick's constant term also here. So only A option is correct here. Then there is this scientist Walker and Shaw. It gathered basically all the Bond's law, Fick's law, and Rittinger's law in uh, one based on the fact that all these laws they come from one differential equation, which is this. So this equation basically it governs that the all these laws, Bond law, Fick law, Rittinger's law. So the energy, if we talk about the energy, and this will equals to minus Kc, which is constant, into d by d to the power n. So here this n is basically 1 for Kick's law, 1.5, sorry, this is 1.5, 1.5 for Bond's law, and 2 for Rittinger's law. So here if we see in this graph, so when we are plotting this, the size of the particle, which can be in any level, which can be in intermediate grinding, so fine grinding or ultra fine grinding. So the different diameter of the or the final product or the particles diameter. So when we are plotting it against the energy which is required to do so, so when n is equals to 1, Kick's law is it's Kick's law. So we can see this line here. When Bond's law is following, when n equals to 1.5, then this kind of graph it will follow. So when the size or also when Rittinger's law is there, so n equals to 2. So this curve is there. The tangent we are drawing, right? So we are seeing what is the slope of this line. So initially the size is coarser here. So here the size is fine size, smaller size. So when we are grinding, so the particle will from coarse it will convert into fine. So if the grinding operation in the if we are doing, and the energy we require for happen. Yeah. So when we require for grinding from the coarse particle to the smaller finer particle, so if we are doing so, then for uh, Kick's law we are following. So what will going to happen? We need less energy for doing so, and we can see if we are converting from this to this particle size, so less energy will require. But for Bond's law, we need more energy, and for Rittinger's law, it says it takes even more energy. So the slope are here different. So if we see the energy consumption for the and intermediate fine grinding and ultra fine grinding or milling is there for any lignocellulosic biomass, and the different laws are given that this will follow different slopes will be there, so they will follow different trends when we are doing so, when we are grinding any particle, and we are measuring the energy. So here if we see, if we are doing the ultra fine milling or very fine milling we are doing, that means we need higher energy to do so. So if we see this slope, so obviously this slope is higher. So we can say for doing ultra fine milling, we need more energy as compared to the intermediate milling. Okay, so here for this question, answer is first, that energy is directly proportional, energy for size reduction is directly proportional to the particles initial size. Okay, let's solve this question. So we have the corn variety V1 with an average grain size is 20 mm, needs to be crushed to an average particle size of 5 mm, and it requires to do so 18 kilojoule per kg of the energy for this unit operation. If other conditions we are keeping the constant, then what is the energy required for V2 variety of the corn if we are reducing the size from 25 to 3 based on the Bond's law? So anyone who would like to solve this question? So what is the Bond's law formula? Bond's law is, formula is here. So it is saying that energy will be directly proportional to the work used to reduce the particle is proportional to the square root of the diameter. So this is the square root. So put this Bond's law and solve this question. Okay, let's solve this question. So we have this corn variety V1. So when we have this corn variety V1, it is initially its size is 20 mm kernels and it is crushed to 5 mm particles, right? And it needed to do so, it needed 18 kilojoule per kg. But now we need to find that if for variety V2 of corn, we are reducing size from 25 to 3, then how much energy we'll need if we are following the Bond's law. So the initial particle size for V1 is 20 mm. The final particle size of corn V1 equals to 5 mm. Then initial particle size of V2 equals to 25 mm and final particle size of V2 equals to 3 mm. That is the given data. And also energy required for V1 is 18 kilojoule per kg. When we are following the Bond's law says equals to Bond's constant multiply by 1 upon under root xp minus 1 upon under root xf. So xp is basically the final size of the particle and xf is the initial one. So this is for E. Now we can write this for E1. E1 equals to kb 1 upon xp1 minus 1 upon xf1. So 1 up multiply by 1 upon under root x p1 minus 1 upon under root x f1 f for 1. Then we can write for E2 also the same equation. So E2 will be E2 equals to, since we are saying that the other conditions are keeping the constant, so this kb will be same for this E2 1 upon under root xp2 minus 1 upon under root xf2. So if we will divide E1 by E2, so this kb will be cancelled out. So what we'll get after solving this equation? E1 by E2 equals to 1 upon root xp1 minus 1 upon root xf1 divided by 1 upon root xp2 minus 1 upon root xf2. So we know already that P1 is basically 5 from the given data, that P1 is basically 5 and x1 is 20. So 1 upon root 5 minus 1 upon root 20 divided by 1 upon root 3 minus 1 upon root 25. This also given that for variety V2 we are reducing the size from 25 to 3. So xp2 will be 3 and xf2 will be 25. So 1 upon under root 5 will be, so under root 5 is 1 upon 2.24. Under root 5 value, if we resolve, it will be 2.24 minus 1 upon under root 20. So under root 20 is 4.47 divided by 1 upon under root 3. So under root 3 is 1.73 and minus 1 upon under root 25. Under root 25 is 5. So here in the question it is given E1 equals to 18. So 18 by E2 equals to 1 upon 22.24, which is 0.446 minus 1 upon 4.47, which is 0.224 divided by 1 upon 1.73, which is equals to 0.578 minus 1 upon 5, which is 0.2. So it will, this equation become this here, and when we are solving, when we are doing minus, subtracting 0.446 minus 0.224, so it will give 0.222 divided by 0.578 minus 0.2, which is 0.378. So this we got, and when we are dividing 0.222 divided by 0.378, it will give 0.587. So this equation became 18 equals to 18 divided by E2 equals to 0.587. So when we are solving this, E2 will be 18 divided by 0.587 and it will give 30.664 kilojoule per kg, which is option B here. Is this question clear to everyone? Can we move to next question? So let's solve this question. A food material is to be grounded from an initial average particle size of 1.5 mm to a final particle size of 0.75. So now 1.5 mm to 0.75 mm we are so the energy required to achieve this size reduction is 25 kilojoule per kg. Now we need to calculate the energy constant kilojoule per kg for this process using Rittinger's law. So we need to calculate basically Kr here. We know what is the formula of Rittinger law when we are calculating the energy. So this is the Rittinger's law. Please put, this is very simple question. We need to just put the values and get the answer. Okay, I'm solving this question. So initial size of the particle is 1.5 mm and we are reducing to 0.75 mm and we needed energy around 25 kilojoule per kg. Now we need to calculate Kr, which is energy constant. So energy constant is equals to E divided by 1 upon xp minus 1 upon xf. for the Rittinger's law. So Kr will be equals to energy, which is 25 divided by 1 upon xp. Xp is final particle size, which is 0.75, minus 1 upon xf, which is initial particle size, which is 1.5. So it will be equals to 25 divided by 1 upon 0.75. So 1 upon 0.75 will be 1.33 minus 1 upon 1.5. So 1 upon 1.5 will be 0.667. So when we minus 1.33 minus 0.667, it will be 0.663. So 25 divided by 0.663 will be 37.71 kilojoule mm per kg. So here answer is B here. Is this question clear to everyone? Okay, we are moving to this question now. Which among the following statement are correct with respect to the membrane processes? So statement 1 is pressure is used as the driving force for separation. Second is suspended solids are separated from liquids. Third is membrane with small pore size are used for microfiltration. And fourth is they are not used for food processing application. Anyone who knows the answer for this question, or anyone who want to guess any option? So Shiva is saying B, 1, 2, and 3. Okay, let's see. So he's correct. So basically this membrane processes are usually we have different membranes like microfiltration, ultrafiltration, reverse osmosis, and what they will do, they'll pass certain molecules. So the water molecules are very small, so it will pass, and other particles they have the different uh, sizes. So they will separate based on their particle size or the molecule size. So in different type of the membranes, they have the different pore size. So based on that, they'll allow certain molecules to pass and they'll reject certain molecules. So the membrane processes they include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, and it relies basically on the pressure to drive the separation process. So suppose here solution A and B is coming and it will be under pressure. So the particle size of solution B, it is small, so it passed through this membrane and solution A separates out differently. So basically the pressure force the liquid or the feed through the membrane where only specific components will pass through while other will be retained. So membrane processes are extensively basically used in the food processing, like for separation, for clarification, for concentration without heat or chemicals. So this is used in fruit juice clarification, like dairy processing, whey demineralization, sugar refining, and wine and beer production also. So basically this statement 4, which is saying they are not used in food processing application, is wrong. And statement 1, which is saying that the pressure is used as a driving force for separation, which is correct. Then we have, as we discussed, that microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. And based on the different sizes, they can separate different particles. So it is the chart is basically given that in membrane, in microfiltration, what all we can separate. So here is the bigger particle size, and here is the smaller particle size. So here is a macro, micro, then basically ionic, till ionic it is going. So smaller particle size it is going. So the particle which is visible to the naked eyes, they'll be separated by mostly all these four kind of membranes. And then optical microscope, we can see those can also be separated by microfiltration. But ultrafiltration separates even more smaller particles, like it can even separate the viruses, gelatin, etc. And nanofiltration even separates more smaller particles like dyes and other things. And in reverse osmosis, basically the ions, which are metal ions and atomic radius particles, can be separated. So microfiltration membranes in particular, they are designed to remove the suspended solids and the larger particles from the liquids. So the microfiltration, it refers to the filtration of the liquid suspension through a membrane with pores around zero point 0.1 to 10 micrometer in diameter, and it retains basically the microorganisms, large colloidal particles, other suspended particles from the processed liquid while transmitting the solutes which are smaller than the pore membrane. So smaller will be passed through, and the bigger particles will be retained. So the molecular weight cutoff here is 10 to the power 4 kilodalton in microfiltration case. And here we can see that milk is being separated uh, in the different type of the membranes like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So reverse osmosis, in this, very fine uh, like very fine separation is there. In nanofiltration only it will pass around nanoparticles. So like that is there. And it is here the comparison of different filtration methods like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So if we see the membrane type, in basically microfiltration, we use asymmetric. In ultrafiltration, we can use both symmetric and asymmetric. Whereas in nano and reverse osmosis, we use basically the asymmetric thin film composites. And the pore size, if we see basically, in microfiltration, it is 0.1 to 100 micrometer. But if we see in the ultrafiltration, it is very small, 0.20022 to 0.1 micrometer. And even if we talk about the nanofiltration, it is even more small, which is 0.5 to 1 nm. And in reverse osmosis, it is non-porous basically. And if we see the molecular weight cutoff, so it is in microfiltration, it is around 10,000 kilodalton, and ultrafiltration it is like very small, 1 to 100 kilodalton, and in nanofiltration only 1 kilodalton, and reverse osmosis even smaller, which is zero point 0.1 kilodalton. And if we talk about the thickness and other things, we can discuss. And if main is how much which particles they are rejecting. So microfiltration, it rejects basically the bacteria, clays, and the particulates. In ultrafiltration, it basically separates macromolecules, proteins, polysaccharides, and viruses. And in nanofiltration, it separates basically the higher molecular weight compounds, monosaccharides, disaccharides, oligosaccharides, and multivalent ions. And in reverse osmosis, it separates basically the higher molecular weight compounds, lower molecular weight compounds, sodium chloride, glucose, and amino acids. So it is for very fine separation. And if we see the operating process, so operating pressure in microfiltration is smaller, then in ultrafiltration it is more, and in nanofiltration it is even more. And if we see in the reverse osmosis, it is even more. So if we talk about here our options, So this membrane processes, it is basically separating the suspended solids from the liquids, which is option true. And we talked about microfiltration, that the membrane with small pore sizes are used for microfiltration, which is also correct. So here option 1, 2, and 3 are correct and not the fourth one as we discussed. Now let's discuss in brief about reverse osmosis process. So in reverse osmosis, basically it is the separation technique in which we are applying here the pressure. So pressure is applied to a solution. So this solution is there. So in this pressure we are applying, and because of the pressure we are applying, this solvent is basically will pass through this semi-permeable membrane. So this solution will, this solvent will pass through from the higher concentration towards its lower concentration. Sorry, solute will go from the higher concentration to lower. So solute will go from the higher concentration to the lower, and the solvent will go through this semi-permeable membrane from a lower concentration to a higher concentration, leaving behind the solute. So this is very important to remember that in reverse osmosis, what will happen? The solute, if we talk about solute, where its concentration will be higher, it will go from higher to lower concentration because it can pass through this semi-permeable membrane, and where its concentration is higher, it will go obviously from the towards the lower uh, concentration. So if we are talking about in terms of solute, but if we are talking in terms about the solvent, so that will be reversed, which is from low concentration towards it higher concentration it will go. That means it will dilution is there. It will come so solute will be diluted basically because solute is going from the higher concentration towards its lower concentration where solvent is more. So where solvent is more, solute will go towards that when the pressure is applied. So the membrane allows basically the passage of small solution components such as the fresh water while preventing the passage of the larger molecules. So if we are using the semi-permeable membrane, like suppose we have the wastewater treatment plant. So there what we use such kind of the semi-permeable membrane where the salts and other impurities cannot pass through the membrane. So what will happen? It will retain on the membrane, and the uh, solvent, which is the water, it can pass when the pressure is applied. So we can get the fresh water. So it facilitates the passage of water molecules while filtering out the salt ions or similar sized molecules. So that is used in the filtration of the saline water or the saline solution. So this way we can get the clean water. So if we have the solution which is having water plus salts, and if we are applying the pressure in reverse osmosis, so water will flow here and all these salts will be retained here. This is the reverse osmosis process. Okay, let's discuss about this question. In this question, we have column 1, which is having the 4 process operations, food process operations like filtration, centrifugation, extraction, and decantation. In column 2, we have their functions. So separation of the two immiscible liquids, or the separating solids from liquids, separating cream from milk, or removing oil from the oil seeds. So anyone who would like to match this from column 1 to column 2? Sohan B, Anju B, Shiva B. Okay. So you three guys are telling correct. So B is the correct answer here. So filtration is basically the process of removing the solid particles suspended in the liquid or the gas by passing the mixture through a porous medium, which is filter paper or membrane. And then the centrifugation, what happens? It uses a centrifugal force to separate the components based on the differences in the densities. So it commonly used for food processing operation in the separation of the cream from the fat. So fat rich cream will because it is lighter, so it will separate from the milk or the milk liquid. Then extraction. So this is the filtration process. So when we put the liquid or the solution, we are putting. So when we put the filter paper, so only the clear liquid will comes like we can collect, and the solids which can be trapped into the filter paper, it can be here. And then centrifugation, we can put it into the solution, we can put it into the centrifuge machine, and we can separate based on the densities. So the lighter will be at top and heavier will be at the bottom. Then extraction process is there. So extraction we can do in which there is a separation of one substance from a mixture using a solvent by either the physical means or the mechanical means, like mechanical press we use. So we use heavy pressure to extract the oil from the oil seed. So in oil seed processing, extraction is basically used to remove the oil from the seeds such as the soybean seeds or the sunflower seeds by using the mechanical pressing operation, and sometimes we use the chemical solvents also to extract the oils from the oil seeds. Then decantation process is there, which separates these two immiscible liquids like the oil and water. So what we can do by allowing, we have this based on the density, there is a separation. So by allowing denser liquid to settle at the bottom, and then the pouring of this lighter liquid, that is decantation. And another operation for separation is sifting or sieving, which separates particles based on the size, like the flour from the husk, which we do in the daily life also. So basically filtration is related to the solid separation from the liquids. Then centrifugation is for the cream separation from the milk. Then extraction is for the oils separation from the oil seeds, and decantation separating two immiscible liquids. So option B is correct here. Let's discuss this question, which is match the column 1. In column 1, we have the food formulation steps like concept development, prototyping, ingredient selection, and preliminary trials. In column 2, we have the description. So we need to match column 1 with column 2. Anyone who would like to answer this question? Shiva is saying B. Vidnyasa also B. Okay, let's see. So you guys correct. B is the correct answer here. So there are different steps when we are formulating or when we are developing a food product. So concept development, basically, then selection of the ingredients, then preliminary trials, then prototyping and testing, and then sensory tasting, and then upscale final stage. upscaling of the food product. So in the concept development, which is also the initial step, it basically all about the understanding the consumer needs and then identifying the market gaps and brainstorming the ideas for new product development or improvement in the existing product. So we need to check the feasibility for its that the product and the technology is matching. So the technical feasibility we need to see. Then it should be financially feasible also, that the product should be cost effective also. The raw material cost and the operation cost should be feasible. Then operational feasibility also. So that means that uh, product we are developing and the process which we are following, can be scalable, and we can also transport it properly, and we can process it properly in the industry also. That is, it should the product should be like that. Then ingredient selection, after that we do ingredient selection. So ingredient selection is important because we need to select here the raw materials. So raw materials is being choose based on what functional requirement we have, or it should be compatible with the uh, other raw materials which we are using. So all the raw materials should be compatible with each other, and it should also contribute to the desired product attributes. It can be both the nutritional uh, attributes, or it can also be the organoleptic or sensory attributes. So there should be the interaction between these ingredients, and they should be like together when they together with all these ingredients are there. So they should not produce any negative effect with the texture, flavor, or it should not produce any allergic compounds, or it should be like basically compatible with each other. Then we do the primarily analysis or the trials, where we do just the small scale experiments to test the feasibility of the product idea. So this stage is basically used to identify the potential challenges and validate the ingredients interactions and refine the initial formulations before moving to the pilot scale prototyping. So after that, we do the prototyping, which involves basically the preliminary version of the product at a pilot scale. We check and we take the feedback and we incorporate that feedback, and we improve the product and based or improve the concept, and we do this primary preliminary trials also. And then there is a sensory tasting. So after that, we check that okay, the food is satisfying the nutritional demand, but whether it is satisfying the sensory and economic demands also. So here we do tests like hedonic scale testing, and we do the quantitative descriptive analysis. Then statistical methods we use like ANOVA or preference mapping to analyze the sensory data. Then after that, large is the upscaling, where the industrial machines will put and try to produce a large amount with the minimum losses. And here we are basically automating the process so that the consistent and high quality and the safe product can be reached to the customer's hand. So here are the all steps from product or the concept development to nutritional or ingredient selection, then the designing or the prototyping, then process we for design, then development will be there. After testing, then it will be iterated, like if the product is failed in this step, like some feedback will be there, then again we'll start from here. So we'll again change the formulation, and we can again then again go for testing, and then based on the feedback, when the final when the product will be passed from this testing step, then it will go for the finally the upscaling of the product. So here the concept development is basically related to the understanding of the customer needs and ideation. And then prototyping is related to the optimizing the formulations at the pilot scale. Then ingredient selection is basically related to evaluation of the interactions and the functional properties. And finally, preliminary trials is related to conducting the small scale experiments, which is option B is correct here. Let's move to the next question. So which of the following statement is are correct with respect to the formulation of the food product? So statement 1 is telling about the functional properties of the ingredients which are critical for achieving desired food stability, and statement 2 is saying that functional properties like water holding capacity prevent synergesis and phase separation. Anyone who would like to answer this question? So Shiva is saying B here, C here. C, which is both 1 and 2 are correct. So he is correct. Both 1 and 2 are correct. So functional properties of the ingredients like this emulsification, gelation, water holding capacity and forming, it plays a pivotal role or the crucial role in maintaining the food stability, because whatever we are adding these the food additives like the emulsifiers, gelation agents or stabilizers, this water hold like the forming agents, they will try to maintain overall food stability, which is statement 1 is correct. And this water holding capacity, basically it is the ability of the ingredient, any ingredient we are adding like protein or the polysaccharides, which can bind or retain, bind, and also it can retain some water, so which is very crucial for preventing the undesired phenomena like synergesis, where separation of liquid is there from a gel or semi-solid matrix like water pooling on the surface of the yogurt, and phase separation process, which is separation of the two immiscible components like the oil and water in the absence of the emulsifying agents or in the absence of the proper emulsification. So statement 1 and 2 both are correct, that functional properties of the ingredients very important to achieve the desired food stability, and water holding capacity, it basically if it's good, so it will prevent the synergesis and also the phase separation. Okay, let's solve this question, that we have the multigrain beverage premix which contains 40% barley. So it has 40% barley, then 30% millet, 20% quinoa and 10% of pea. So overall batch size is 500 kg. So how much barley, millet and quinoa and pea we will require? So this is very simple question. Please try to solve this question. Anyone who is solving this question? Anju is saying D is correct answer. Then Sohan is saying C. Okay, let's see. So D is the correct answer here. So as we know that the amount of the barley is 40% in the formulation, millet is 30%, quinoa is 20%, and pea is 10% in the formulation. So mass ratio of the ingredient is equals to amount in percent divided by 100. So mass of the barley in the formulation will be 40 divided by 100, which will be 0.4. Same for the millet, which is 30%. So 30 divided by 100, it would be 0.3. Then mass ratio of the quinoa will be 20 divided by 100 is 0.2, and mass ratio of the pea in the formulation will be 10 divided by 100, which is 0.1. So this the amount of the ingredient when will be equals to what mass of the total batch is there multiplied by their mass ratios. So amount of the barley in the formulation will be mass ratio, which is 0.4, into total size is 500 kg batch, which is equals to 0.4 into 500 is 200 kg. Then millet is 0.3 mass ratio into 500 kg of the batch. In 500 kg of batch, it is 0.3. So it will be equals to 0.3 into 500, which is 150 kg. Then amount of quinoa in the formulation is 0.2 into 500, which is 100 kg. And for P is 0.1 into 500, which is 50 kg. So answer is D here. I hope this question is clear to all. Let's move to the next question. Let's solve this question. So a fortified rice kernel manufacturer is fortifying the rice flour with the vitamin mineral premixes. So rice flour is fortifying with VMK, which is vitamin mineral premixes, and the concentration of this VMP is mg per kg in 5 different test samples taken from a batch are this. So in the mixed, the fortified rice flour, when we see the VMP amount, so it tested and we got the 5 test results as this here. So we need to tell about the percentage relative standard deviation. Anyone who would like to answer this question? Please solve all these questions with pen and paper with me when I am trying to solve this question. You also please try to solve. Shiva is saying A 1.83. Jitnyasa also A 1.83. Okay, so they both are correct. Let's solve this question. So there is given data which is number of samples n value equals to 5. And when we are calculating the percentage RSD, relative standard deviation, so it is equals to standard deviation divided by mean of data into 100. So here we need to calculate first the standard deviation also, and the second thing is mean of data. So mean of data, how we can calculate? So mean of data is, we have the 5 data sets, which is here we can calculate the mean 12.3 plus 11.9 plus 12.5 plus 2.1 plus 2.2 divided by total is 5. So divide by 5 is equals to, so 12.3 plus 11.9 plus 12.5 plus 12.1 plus 12.2 is equals to 61, and divide by its total number 5. So mean value we got as 12.2. So this value mean of data set we got as 12.2. Now we need to calculate standard deviation. So standard deviation formula is standard deviation square is equals to that whatever is the deviation from the mean for each sample, like xi, which is x1, which is this x1, minus the minus of average value, which is this value. So their minus will be, their subtraction will be squared and they will be summed up, because there is summation for all. divide by n minus 1. So n is 5 minus 1. So this is standard deviation square. So standard deviation square can be equals to here, because here this is, we are putting n equals to 5. So n, which is 5 in the denominator, so n equals to 5. So 5 minus 1 equals to 4. So this formula now become standard deviation square is equals to summation from 1 to 5 bracket, square of sum of the square of whatever is the difference will be there for each samples from the mean. So their sum, their square will do, and then sum will do, and divide by 4 will take. So here, if we see in this table, we have the samples and xi value. Now what we are doing, we are differentiating, sorry, not differentiating, I'm differencing or subtracting, basically better to use subtract word now. So subtracting this each value, which is x1, minus its average, which is 12.2. So 12.3 minus 12.2, which is 0.1. Then 11.9 minus 12.2 is equals to minus 0.3. Then 12.5 minus 12.2 equals to 0.3. Then 12.1 minus 12.2 equals to minus 0.1. And then 12.2 minus 12.2 will be 0. Then its square will be 0.1 square is 0.01. Then minus 0.3 square will be 0.09. Then plus 0.3 square will be 0.09, and minus 0.1 square will be 0.01, and 0 ka square is 0. So now we need to sum all these. So their summation will be 0.2. So when we add all these, 0.01 plus 0.09 plus 0.09, then 0.01, it will be 0.2. So now we can calculate standard deviation. So standard deviation square is equals to the summation of the square of all these values of whatever is the subtraction we got. So that is 0.2 divided by n minus 1, which is 4. So 0.2 divided by 4 is 0.05, and this is the square of standard deviation. So the standard deviation will be under root 0.05, which is 0.224 mg per kg. This we got standard deviation. Now we need to calculate the relative standard deviation. So the relative standard deviation is equals to the percentage of the relative standard deviation is equals to whatever relative deviation we are getting, which is 0.224 divided by the average value, which is 12.2 into 100. So 0.224 divided by 12.2 is 0.01836 into 100. So it is around 1.83%, which is here as option 1. So is this question clear? So also when we have the normal distribution, so the mean, median and mode will rely on the same line. But when we have the left skew kind of the distribution, so what happens? The mean, mode will be the highest, then mean, median, then mean. And when we have the right skew distribution, then the mode will be highest, then median, then then mean will be the highest, then median, and then the mode, because this value is the highest here, na? Okay. And if we see the distribution, it can be, if it has the, it can have broad also like this, and it can have this narrow distribution. So this is less relative error will be there, and in the broad one, the more error will be there, or more standard deviation will be there from the values. Okay, so let's solve this question. We have this question which is about simple latex design. So we have different mathematical tools when we, so it can include mixer designs, response surface methodology, and linear programming. And in the mixer design, we have the simplex lattice design, simplex centroid design, and augmented mixture design. So we are talking here about simple lattice design. So how many experiments will be required in a simple lattice design with 4 ingredients and 2 equal divisions between 0 and 1? Shiva C, which is 10. Okay, let's see. So he's correct basically. So simplex latex design is basically a specific type of mixture design. So it is used to systematically study the effect of various or varying proportion of the ingredients in a mixture. So there is a symmetrical arrangement of the points within the experimental design in this. So it is used in a mixture where we have the sum of all the ingredients like A plus B equals to plus C equals to constant will be there, or sometimes we can say it can be 100. So the number of experiments to calculate here when we do the simplex lattice design, n equals to q plus m minus 1 factorial divided by m factorial multiply q minus 1 factorial. So each component of the mixture takes m plus 1 equally spaced values between 0 to 1. Suppose if we have the xi value can be equals to 0, 1 upon m, 2 upon m, 4, so it can be equals to 1. So as we said, the sum will be of the all the proportion can be equals to constant or 1. So all the mixture involves these proportion are used in experimental design like this. So this is a simple simplex lattice design. So here all the points are there in the this sides, and if there is simplex, this first design simplex centroid design, there is one more point which is at the center. So let's solve this question. As we discussed that the formula to calculate the number of experiments, so here also it is saying how, question is also asking about how many experiments. So number of experiments n equals to q plus m minus 1 factorial divided by m factorial multiply q minus 1 factorial, right? Here 4 ingredients are given, so 4 q are given and 2 equal divisions between 0.0 to 1. So 0 to 1, how many equal divisions are there? 2. So m value is equals to 2. So the proportion will become in between 0. So proportion which is xi. So as we calculated here, xi is 0, 1 upon m, 2 upon m like that. So this is first is 0, then second becomes, second is 1 upon m. 1 upon m matlab 1 upon 2, then 2 upon m, which is 2 upon 2. So overall it becomes 0, 0.5 and 1. These are the proportions. So number of experiments, if we see n equals to q, q is number of ingredients which is 4 plus m, which is how much division is there. So 2 equal divisions are there. So m equals to 2. So 4 plus 2 minus 1 factorial divided by m, which is 2 factorial multiply q minus 1, which is q is 4, 4 minus 1 factorial. So 4 plus 2, 6 minus 1, which is 5 factorial divided by 2 factorial multiplied by 4 minus 1, which is 3 factorial. So 5 factorial is 1 into 2 into 3 into 4 into 5. So which will be 1 into 2 into 3 into 4 into 5. So it is basically 120. This. So 120 divided by 2 factorial, which is 1 into 2 is 2 into 3 factorial, which is 1 into 2 into 3, which is 6. So 120 divided by 2 into 6, which is 12. So 120 divided by 12, which is equals to 10. Is this question clear to everyone? Here q equals to 4 is there, so it means that this geometry is kind of a tetrahedron kind of geometry. So if q equals to 3 will be there, would have been there, so what could have been there? Like triangular kind of geometry could have, we have imagined like that. Here now we have the mathematical tools in column 1, and in column 2 we have their applications. So we need to match like linear programming, RSM, response surface methodology, simplex centroid design, and preference mapping. In column 2 we have the application like optimizing cost and nutrition balance. Then B is measurement, in measuring interactions effects among variables. C is evaluating all possible ingredient combinations, and D is relating consumers liking to the product attributes. Anyone who would like to answer this question? Aman, I think B. Okay, Aman is saying that B can be correct. Then Sohan is saying C can be correct. Okay, let's see. So here D is correct answer. Let's understand why. So linear programming basically is a mathematical tool which is used for optimizing the cost and nutritional balance in the food formulation by determining the most effective combination of the ingredients within the specific constraint. So in 10th 11th class we solve the linear programming. Also if you have taken maths as your subject, so there you could have taken linear programming. So there what was there? So in linear programming we'll have one first equation sum, then second equation we'll have sum, and when we solve this equation we get like this line particularly is for one equation, and this line is for particularly one equation, and they are solving, and when we are plotting in the graph it gives some area. So if less than condition was there, so we got this area like that. So this is basically used for that, for the optimizing of the cost and nutritional balance, and we in the basically that the minimum is the cost and maximum we can get the nutrition balance, like that constants can be there, and we can solve this equation and we can get this value. So here in linear programming, we formulate the problems with the objective function where we define the goals can be that we want to maximize some nutrition, or we can minimize the cost of the operation. That can be our goal. So we formulate the objective function. So in objective function, we can have one equation like that. Then decision variables will be there. So the decision variables will tell the quantity of the ingredients in the food formulation. Suppose X amount is this, Y amount is so. So that is the decision variables. And next is we will have some kind of the constraints that will limit their nutritional requirements. Like we can say that the nutritional should be less than equals to, or it should be greater than equals to. Like that we can put some constraints. So we model and optimize these equations in the form of the linear form, and we can use sometimes some softwares also, and then we interpret the results, and we based on this we can get some result or optimized area, and we can operate our system in that. Whereas in RSM, it is a statistical technique used for optimizing the processes and also the formulations by studying the relationship between multiple independent variables and the dependent variables. So in RSM, when we use it, it has different models also, like CCD model. Then we can use BBD model. So CCD model is basically central composite design, and BBD is box banking design. So we use these methods basically in the RSM, where we can have certain independent variables like time, temperature, loading ratio, and we can have the dependent variables like if we are doing some kind of the extraction, suppose, or of the polyphenols. So we can have time, temperature of the, suppose we are doing the ultrasonic assisted extraction. So the time, temperature, the power, loading ratio of the with the solvent, it can be a basically the independent variable, whereas the response or the dependent variables can be, suppose, DPPH activity or antioxidant activity. Then also the flavonoids, also we can use, suppose, the phenolic contents. So these can be used as a response or the dependent variables. So it helps in measuring the interaction effects among variables and optimizing the processing conditions to achieve the desired product attributes. So this is basically a 3D RSM curve, and this is 2D. So we can have different variables, and what is the interaction effects of different variables. Then we discussed about already the simplex design. This is simplex centroid design. Here is it is a tool for evaluating all possible ingredient combinations in the mixture experiments, ensuring the total composition sums to a fixed value. So here also it is saying that sum should be to a fixed value. So it evaluates responses at the vertices. So like we discussed in, so here it will at the vertices, it will have the point, it will have the at the, so this is the diagram. So here at the vertices it is having this vertices, this vertices, this vertices, then the middle points, then also the center. So it will have these all these points in the formulation of the formulation spaces, and when we calculate the number of the design points, so it can be n equals to 2 to the power q, which is the q components, minus 1 in the simplex centroid design. Whereas we discussed that it is n equals to this number of experiments in the simplex lattice design. And preference mapping is basically used to relate the consumer liking to the product attributes. So it is basically helping the manufacturer to understand the sensory or physical characteristics influence the consumer preferences. So it will be discussed in future, like in the coming slides in detail. So it is basically used to, this preference mapping is basically used to relate the consumer likings to the product attributes. And then simplex centroid design is evaluating all the possible ingredient combinations. RSM is basically measuring the interaction effects among the variables, and linear programming is for optimizing the cost and nutritional balance. Okay, so this is question is on CCD, central composite design. How many experiments run are required for a CCD with three factors and two center points? So anyone who would like to answer this question? This is kind of a RSM. So in RSM, there are two designs, CCD, BPD, like that. So Jitnyasa is saying C here, and Shiva C, Anju C, Sohan C. So everyone is saying C. So you guys are correct. So basically in CCD, which is a central composite design, is an experimental model which is used to build a quadratic model for the response surface. So it models basically build a quadratic model. So it consists of three type of points: the factorial points, which are at the corner. So it is designed like plus minus one code, and then axial points. So the points which are at the axis. So it can be plus minus alpha levels. We from this we can denote. Uh, and these the factorial points, the axial points, and the center points, they'll form a quadratic response model, and we can finally put in the this surface, this kind of graphs, response surface graphs. So here, given as that number of the factors are 3 and the number of center points are 2, and in BBD we have the number of experiments n equals to 2 to the power k plus 2k plus c. So here k are the number of factors, and c is the number of center points. So when we put uh, all the given values, so the number of experiments n equals to 2 to the power 3, which is number of factors, which is this. So plus 2 into k, which is 3, so number of factors, and plus center points, which are 2. So 2 to the power 3, which is 8, 2 into 3, which is 6, and plus 2. So overall it is 16. So in central composite design, we take these are the at the corners, this is at the axis, and this is at the center. Whereas if we talk about in the box banking design, so it is a 3-level response surface methodology. So it is used to evaluate the relationship between multiple formulation variables and the target response while minimizing the number of experimental trials. So it helps identifying the optimal combination of the ingredients or processing parameters to achieve desired food quality or performance. And here, in this case, number of experimental runs n will be equals to 2 into factors multiplied by k minus 1, which is factor minus 1, plus c, which is center points. So in BBD, the number of experiments will be lesser than this CCD model. Here, if we see in BBD, we take points in the middle of the this side and all these sides, and the here in the center. One more design is there, which is full factorial design. So in full factorial design, it basically takes all possible combinations of the factor level to assess main effect and the interaction effect comprehensively. So it will follow the logic that responses depend on individual factors and their joint influences. So it takes all 2 to the power k runs for any experiment. So I am saying 2 because mostly we use 2-level case. So when m equals to 2, which is a 2-level case, which is plus 1 and minus 1 settings, so the runs can go up to 2 to the power k, which is number of factors. So here the maximum runs will be there, like all runs it will, all centers also it has taken, in middle also it has taken. So it has taken all kind of runs. So here we solved an answer we got as 60. Okay, let's move to this question. Assertion is preference mapping is only applicable to sensory data, and reason is it involves statistical analysis of the consumer behavior, sorry, consumer choice without liking them to product attributes. So we need to tell here about assertion and reason. So Aman saying D and Shiva saying B. D, B. Okay, let's see. So here C is the correct answer, that the assertion is true but the reason is false. So basically the preference mapping primarily analyzes the sensory data to relate the consumer preferences, likings or the scores to sensory attributes of the product like sweetness, texture or the aroma. So statement 1, which is assertion, is correct. And basically it is a critical tool in product development to understand how the sensory characteristics drive consumer choices. So basically the consumer choices are here linked with the product's characteristics, and it takes those data and do the statistical analysis like PCA, PLS, which is PLS kind of regression, and PCA it will plot and to identify that how the sensory or the physical attributes it influences the liking scores. So it can be like this. This is kind of a PCA plot. So it tells that okay, different customers has chosen or have different liking behavior. Some has this, some has this. It tells how much it is like it will group all the behaviors of the consumer liking. So preference mapping, it can be internal preference mapping or external preference mapping. So if internal preference mapping, it analyzes only consumer preference data using techniques like PCA and analyze to identify the patterns and grouping in the preferences. Whereas in external preference mapping, it links the consumer preference data to product attribute also using the regression or correlation techniques. So in internal preference mapping, only PC it will plot and separate the groups. But in external preference mapping, it will also relate to the regressions or the models like PLSR model, partial least square regression model, and it identifies how specific the sensory or the computational attributes drive consumer liking, aiding in target product optimization. So here it links with, not without, it should be with linking with the product attributes also. So assertion is true, but the reason is false. Okay, let's solve this question. What should be the quantity of rice flour in designed fortified rice noodles formulations, which is from using the rice flour? So here the rice content will be 3.2 mg per 100 gram, and moringa powder where the iron content is 6 mg per 100 gram to meet the iron content requirement of at least 4.45 mg per 100 gram. The objective is to maximize the amount of the rice flour in the formulation while satisfying all the constraints. So this kind of equation is an example of linear programming, which we discussed before. So usually here we have this uh, condition constraints like maximizing, goal is to maximize. So the objective is here to maximize the amount of the rice flour in the formulation to satisfy and while satisfying the constraints. So the constraints is that in the final product we should have the iron content at least 4.45 mg per 100 grams, and the decision variables is given as that rice flour should be 3.2 mg per 100 gram and the moringa powder iron content should be 6.0 mg per 100 grams. We need to meet the requirement with matching or putting those into particular amount to get this 4.45 mg per 100 gram of at least iron content. So Shiva has already solved and he got the answer as 55.36. And Aman solved, he got the answer as 68.52. And Jidnyasa got the answer as 72.01. Okay, let's see the solution. So answer is B. Let's solve this question. So we got that iron content in the rice flour is 3.2 mg per 100 gram. And in moringa, it is 6 mg per 100 gram. And in fortified rice noodles, we should get 4.45 mg per 100 gram. And since it's a case of linear programming, the total sum will be around, it should be some constant. And we are here saying that overall, the amount is from 100 grams. So the total quantity of the product is 100 grams. So the iron content equation would be now 3.2 XR, which is the for rice flour. So the iron content, which is 3.2 mg per 100 gram. So 3.2 into XR plus 6 in XM equals to, when we are using 4.4, which is equals to 4.45 in the total rice noodle, we should get this amount 4.45 into the total quantity of the product is 100 grams. So as a total quantity also is 100 grams, so the individual, which is when we are mixing the rice flour proportion with the moringa, the sum should be equals to 100. So XR plus XM is equals to 100. So here from XM would be 100 minus XR, and this we can put it into equation 1. So we can solve here 3.2 XR plus 6 into XM, which is 100 minus from 2 we got 100 minus XR equals to 4.45 into 100, which is 445. So now we solve 3.2 XR plus 6 into 100 is 600 minus 6 into XR is minus 6 XR equals to 445. When we minus or subtract 3.2 minus 6 XR, 6 both XR term this. So it will be 3.2 minus 6 will be 2 point minus 2.8 XR plus 600 equals to 445. So minus 2.8 XR equals to 445 minus this 600, which is minus 155. So XR would be minus 155 divided by minus 2.8, which is 55.36 gram. So this is the amount of the rice flour we are adding, 55.36 gram, which is having 3.2 mg per 100 gram of the iron content to this moringa powder. So the moringa powder will be 100 minus this value. But we need to know only the rice flour amount, which is 55.36. Okay, so here is the statement regarding synbiotic foods. So statement 1 says that the synbiotic foods are more effective than the probiotic alone, and synbiotic foods combine bacterial beneficial bacteria with the prebiotics that enhances the bacterial growth. This question, anyone who would like to answer? Aman C, Anju C, Shiva B. Okay. Let's see. So C is correct here. So what happens? Symbiotic foods are those foods which combine the probiotic, which is a live beneficial bacteria, with the prebiotics, non-digestible fibers that serve as a food for probiotics. So they will be mixed and they will be put into symbiotic food. So the live microorganisms are being used, mixed, and the substrate also is used, and it will provide health benefits to the human. So this combination will enhance the survival, colonization, and activity of the probiotics in the gut, so making the symbiotic food more effective at the improving the gut health and overall well-being compared to the probiotics alone. So statement 1 is correct here and 2 is also correct here. So both are correct. So uh, the probiotic food or the probiotic microorganisms, it can be both dairy based matrix and on non dairy based matrix, and it can be put for the human health, and it can also it can provide health benefits like it can control the intestinal infection, it can enhance the gut strength, it prevents the osteoporosis, cholesteremia, diarrhea, and other like urogent, urogenital infections, and then it helps in improving the immune system. So immunostimulatory effects also, anti-carcinogenic, anti-mutagenic, anti-hyperglycemic effect, anti-diabetic, and anti-fatigue effects it shows. So it can have different examples like when we put yogurt with the inulin. So yogurt can have the live probiotic culture, and the inulin, which is prebiotic, can help as a so it can form symbiotic foods. And fortified dairy products like milk or cheese enriched with the live probiotics and prebiotics fibers, and functional beverages like which can have both the probiotics and the prebiotics, fruit juices like that. And if you are using the dairy based metrics, it can make like some people may have this uh, indigestion towards milk is there, so it cannot be effective for those people. So non-dairy based matrix can be used by those people where they don't have that, well, where they have the allergy with the milk, so they can go for non-dairy based matrices also for the foods for symbiotic product. Okay, so let's now discuss about 3D food printers or the 3D printing of the food. So assertion is 3D printed foods can deliver precise amount of the nutrition. Reason is saying the printing process ensures accurate deposition of ingredients based on digital designs. Okay, Shiva, Aman, and Anju A. Okay, so you guys are correct. So 3D food printing, it involves basically the layer by layer deposition of the food materials like the pastes and the puree from a digital design, like the computer aided design model, which is like when we make model initially, we'll use the CAD software and we'll make and we'll put into the, we'll give the command to the 3D printer to print based on that model. So it enables the precise control over the shape, texture, composition of the food product to create a 3D model. So 3D printer basically usually put layer by layer, will deposit and make the food product based on this model which we provide. So both the assertion and the reason are correct here. And reason is also the correct explanation of the assertion. So we can also deliver the precise amount of the nutrients based on the which model we are making. So this is the example of, like, suppose this is a chocolate structure. So we can provide the different designs and it can make layer by layer deposition of the chocolate layer. So 3D printing, food printing, it allows basically the customization of the nutrient content in the food to meet the specific dietary needs of the children. So 3D food printed, it operates using the digital designs, which controls the exact quantity and placement of the ingredients during the deposition. This accurately ensures that the nutrients are distributed uniformly and also in the precise amount as specified in the design, making it a reliable tool for delivery of the precise nutrients, ensuring the food security. Okay, let's discuss this question about statement which is correct regarding the extrusion based 3D printing. So, which statement can be correct? It is most commonly used technology in food manufacturing. Second, it requires material with high viscosity and flowability, and it cannot be used for multi-material foods, and it works through layer by layer deposition. About extrusion based 3D printing. Okay, so Aman is saying B, Shiva also B, 1, 2, and 4. Anju also B. So you guys are correct. So this is also kind of 3D printed food model. So extrusion based 3D printing is most widely used method for food manufacturing due to its versatility and ability to handle various food materials like dough, chocolates, and the purees. For better extrusion, the material must have the high viscosity and sufficient flowability for better product integrity, as extrusion based 3D food printing works through layer by layer deposition method. So obviously layer by layer deposition method, and it is used in multi food systems because like purees, chocolates, dough, there are multiple food systems. So then it requires obviously high viscosity material with good flowability, and obviously it is used commonly used techniques in the food manufacturing. This 3D based, this extrusion based 3D printing can handle multi-layered foods by using even multiple nozzles or the cartridge. So we can make a different layer first time, and then second layer is can be of different material, then third layer can be of different. This kind of multi-layered materials, multi-materials also we can use sometimes in extrusion based 3D printing. So this allows for the combination of different textures, colors, and flavors in the single printed product we can get. So this is the basically what happens in the extrusion based 3D printing. So it basically usually a 3D printer is like here is basically the main extrusion assembly which is connected with a motor. So here is its nozzle. So here in this area, this kind of system can be there where feeding zone in feed zone feed will come, and then it will be compressed and the flow control will be there, and from the nozzle the food will come out and it will deposit layer by layer on this platform. So here are the some 3D printers. So this is a basically extrusion based 3D food printer figures are there. So here first is the Cartesian, and second is for the delta. This is the polar. This is the sacra. So this is the basically syringe type, I guess. This is the pneumatic, and this is the extrusion based. So these are different 3D printing models. So here also there are different 3D printers. So it is the general extrusion is doing. So here from extrusion from this nozzle, it is coming and depositing. So single extrusion, single nozzle is there. So it is producing this semi-solid food ink that supports the some food structure. Then there is coaxial extrusion. So here there is like an inner outer connecting nozzle is there like this. So A1 is this, one is this. It is coming and it can form the inner layer and outer layer like this. So it can couple two materials in one encapsulated filament. And then dual extrusion like this is there. So here is the fat, here is the blood, and it is making a meat kind of product. And this is the free form reversible embedding of the suspended hydrogels. So this is a needle kind of nozzle is there, and it is putting and forming some hydrogel kind of assembly. Like this is making the heart kind of, it is printing heart kind of structure. Okay, so this is the extrusion based 3D model in which answer B is correct. 1, 2, and 4 statement are correct. Okay, let's discuss this question. We have in column 1 3D printed components like nozzles, mixing chambers, drive system, flow sensors, and in column 2 its functions are given. So anyone who would like to match? Aman, B. Okay, let's see. So he's correct. So there can be different components in the 3D printer. So it can, one is control circuit. So this integrates the computer and the printer, allowing the printer to understand and execute the command given by the computer. Then there is motor, where the power, it basically powers the movement of the extruder and printing bed. Then filaments are there, like this is a system. So here it will connect it to the computer, and it, which is the control system. Then power supply is there and motor is there. Then filaments are there which provide the material such as the plastic or the food paste that is extruded to create the object. So some filament is there, so that can be printed here. So the drive system is there, which includes the motor and the mechanism, and that control the precise movement of the printers component like nozzle, bed, printing bed. So according to the digital design, so based on the digital design, that motor will going to basically regulate. Then the mixing chamber is where the mixing of the ingredients are being done, and uh, they are homogenized to ensure the proper texture or the consistency and the composition of the materials. So before it is being extruded through the nozzle. So this is essential for achieving uniform consistency and the desired texture. Then we have feed rollers. So it assists in the feeding the filament or the food material into the extruder, ensuring a steady and controlled flow. Then flow sensors are there which track the rate at which the material is extruded, ensuring uniform deposition and preventing issues like clogging or inconsistent flow. Pressure regulators are there to control the pressure at which the material is extruded, ensuring the smooth and even deposition. The nozzles are there, which is a part of the 3D printer responsible for the extruding the materials and depositing it into layer by layer to build the final structure. The nozzle size can vary depending on the resolution and details which are required for the printing. Then printing platform is there, which is a 3-axis stage Cartesian coordinates. So here aligning the movement along the x, y, and z axis, enabling the creation of the 3D objects. Then dispensing or sintering unit, which is responsible for extruding or solidifying the material as it is deposited. Then user interface, which provide an interface for the user to interact with the printer, inputting commands, adjusting settings, and monitoring the progress. So here is this display. So nozzle is connected to deposition of the material layer by layer. Then mixing chamber is for ensuring the material consistency before the extrusion. Then driving system is for the controlling the precise movement of the controller of the printer, and flow sensors monitors the material flow rate. Like these are the different steps we can have in the 3D printer. So we can have some model, and we'll put that model in the software, and we will put into the form of the codes, and then food recipe we can select, and based on that 3D printing is printing, and the cookies is being printed deposition by deposition. Then we can put into further processing like baking, frying, etc. So these are the different food samples which are 3D printed, like this. This is a thin cracker, then pasta, then bread roll, pizza, oat cereals, chocolates. So now, what is the primary application of selective layer sintering in 3D food printing? So we need to tell about selective laser sintering. So which option can be correct? Anyone who would like to answer this question? Anju C, Shiva B, Aman A. Okay, let's see. So selective laser sintering is basically, it is having this kind of laser source, and there will be some scanner system, and the laser wave beam will come, and the powdered products will be basically it is used to make the 3D printed food product. Like this is the three sintering selective laser sintering based 3D food printing. From this it produced this particular food product. So answer D is correct here, that printing integrates design with lipid-based food. So basically this selective laser sintering is basically a high-powered laser. It used, like this is a high-powered laser, to selectively fuse the powdered materials layer by layer to form the 3D structure. So it used powder layers. So the laser scans each layer of the powder and heating it to a point where the particles will going to sinter together and form a solid object. So the powders, they'll go, the layers from made from the powders, it will be heated up, and a solid object will be made out of that. So this process is repeated layer by layer until the object is completed. So it is particularly suited for powder-based food material which has low melting point and easily sintered, such as sugars, powdered chocolates or other dry ingredients and can combine multiple materials in a single process. So here this technique is most effectively used for creating the complex integrated shape from powdered food ingredients, combining multiple powder materials to create multi-material foods with unique texture and the flavor. So this it, option is wrong, that it ejects droplet of liquid materials. Also, it doesn't use any liquid binder. The primary application, printing integrate design with lipid foods, basically is used to do this. And producing multi-material foods with powders. It makes food products with powder, but the main one application is the D. So which type of 3D food printing is most suitable material like cheese or dough? Anyone who would like to answer this question? For cheese and dough, most suitable. Binder jetting, extrusion based printing, selective laser sintering, or inkjet printing. Shiva B, extrusion based. Okay. Option D usually involves extrusion based printing, not sintering. So lipid based food is basically not used for in the extrusion. Lipid based food basically they usually we get into the powder form, and when we heat they easily melt and they make a sol like a homogeneous kind of product, and a sol when it is cooled down, then it will become a solid object like that. Yes, that this selective laser sintering, it basically use for the powder, like the powder structure. So the powders if we take usually. So what happens? Here it is saying what is a primary application. So we have done option D correct here. The primary application is for the lipid based, because we are not producing multi-layered food products with powders, like we are making from powders, that is there, but the primary application we use for the lipid based food products. We get the lipids in the powder form and we put, and that is heated and make the solid objects. Obviously the partially we can correct this also, as we discussed. I mean, is it clear? Okay, fine. So uh, this we were discussing this question regarding the dough and cheese, most suitable food product for dough and cheese. As we discussed, this is the extrusion based one. So what happened? Extrusion based printing, it is basically the pushing the material through nozzle and depositing them in layer by layer to create the 3D structure. So this method extrudes basically the semi-solid materials, which is like the dough and the cheese, like the high viscosity materials, like from the nozzle. So it is ideal for dough. Then it is for good for puree and melts like chocolates, cheese, fruit or vegetable purees, then meat purees, milk formulations. So it is good for high viscosity materials which are easily extruded and making them ideal for the cheese and the dough. So this type of printing is widely used for creating the complex shapes and textures in high viscosity material. So extrusion cannot be used for the lipid based products basically, because lipid based products we use in powdered form like that, but here we are using the high viscosity or the semi solid kind of materials for extrusion based printing. So it supports customization in catering, like, and uh, some like basically it is used for formulation or the fortification of the certain kind of diets, but it will not use like it will use all the high viscosity product which are easily extruded, but not the low viscosity inks we cannot use because its speed will be lower down then inkjets basically they are good in high resolution decorations using the liquids or colloidal inks like syrups, sauces and sugars and the chocolate melts, and it is best for the surface patterns on cakes but limited to non-viscous materials and slower for 3D builds. So it uses basically the liquids or colloidal inks, and this binder jetting is basically it deposits the liquid binders onto the food powder. So this is basically the food powders will be there, and in binder jet the liquid binding agent will come, and it will bind the two layers like the starch, sugar, flour, right, the starch, sugars, and the flours to form these bakery items, biscuits, and the snacks. So it enables multi-flavor prints without heat, but requires post-processing and precision power control. Then selective laser sintering, this laser sinters fuses powder like the sugar, chocolates, or the fat. So obviously this, as we know, discussed that is used for fat for high precision candies and creative foods. It suits complex geometries but demands fine powders and expensive equipments. So here answer is the second one, extrusion based printing. So here from the diagram we can understand the differences. So extrusion based printing, here extruder is there which will pass the food through a nozzle. Then binder jetting. So here we see then that here is the binder supply, like the liquid supply of the binder. It will come and the binder will drop over the powder. This powder bed is there. So over this the liquid will come. Selective, this laser sintering, the high power laser source is there, and this laser will come and provide the heat, and this due to melting it makes the solid structure, and then after the cooling it will make solid structure. Whereas in the inkjet printing what happens, basically the food will come through this nozzle, so it is the liquid food is coming in the form of the droplets, it is coming and making the 3D printed object. So so next week what we'll be going to discuss, so in next week, we'll be discussing about the concepts in food manufacturing and industries 4.0, then AI and ML application in food processing, then advanced instrumentation and sensors, and process control and automation, and robotics and future trends in food manufacturing. So I'll upload the respective materials in the on the website. So thank you so much for joining today's class. So if you have any doubt, please feel free to ask. Otherwise, you can leave the meeting, or also do not forget to join the class on next Sunday, same time. So thank you so much, guys, for joining today's class. So I am stopping the recording now. Aman, thank you so much for joining the class and providing your inputs in the class